Okay, here's a second example of indeterminate problems, and this one is strain example number 11. So the problem reads, determine the maximum load P that can be applied to the system shown below based on limiting stresses in wires CD and EF. Take L1 as 40 centimeters, take L2 as 30 centimeters, and B as 30 centimeters. Wire CD is made out of aluminum, and wire EF is made out of magnesium. So given those and the allowable stresses, we're going to go ahead and figure out what the maximum load P is. So the first thing I'll do with this problem is take a look at a free body diagram of the rigid bar. With the rigid bar, excuse me, what we can do is we could recognize that there is an externally applied load P out here. There is a member force in this wire here. It's going to be called P sub EF. And then there is a member force in this wire here that is going to be called P sub CD. We also have reactions over here at point A. So if I scroll up a little bit, and then I can go in here and write that this is a reaction at A in the Y direction. And then this is going to be the reaction at A in the X direction. So what we can do is we can look at statics as our first step in this problem. And we could take the sum of the forces in the X direction, recognize that that should be equal to 0. And what we get is that R sub AX is equal to 0. Then we could take some of the forces in the Y direction, or some of the moments about some point. So we can take the sum of the moments, let's say about point A, that should be equal to 0. We'll take that as positive. And what we end up with is, let's see, P sub CD times 30 centimeters plus P sub EF times 60 centimeters and then minus P acting at a distance of 90 centimeters equals 0. Excuse me. And then finally, we could take the third equation, the sum of the forces in the Y direction, and that should be equal to 0 as well. And when we do that, we get that R sub AY plus P sub CD plus P sub EF minus P equals 0. Now, when we go through and do this, it works out that even if we were to back substitute within these three equations, that we wouldn't be able to solve for all of the unknowns. In fact, it works out here if we treat P as a known value. Even though it's not given to us, we could still treat it as a known because it's an external force. Then we end up with 1, 2, 3, 4 unknown forces. And when we look at it from that point of view, we have 4 unknowns, and we only have 3 equations that we can use coming from statics. So this is a statically indeterminate problem. Okay, what does that mean? That means that we have a problem where we can't solve for internal member forces using the equations of statics alone. And that means we're going to have to use all 3 of our tools in our toolbox in order to come to the final answer. So the first tool is statics. Second tool is geometric compatibility. And the third tool is force deformation relationships, or I called them constitutive relationships in the last example. Same thing. And then after we use those 3 tools, then we'll have to go back and do some substitution, followed by checking to make sure that the values of stress in the wires are below their acceptable levels. So the second step in the solution to this problem is to figure out what our geometric compatibility relationship is going to be. Now, I wish there was an equation that I could point to or a set of steps that would give you a path to follow for every problem, but there just isn't. Let me scroll back up to the top. What's going to happen is that, well, the way I approach these problems is I like to look at the way that the structure is going to deform when it's loaded. Now, we are going to assume that this bar right here is rigid and it doesn't bend in any way when it's loaded. Now, that's not a realistic assumption. There's going to be some bending in there. But we have to make some assumption in order to get to a solution to this problem. So what we're going to assume is that this bar is going to deform like that. It's going to rotate about point A. And it's going to remain straight. It's not going to remain horizontal, but it is going to remain straight. So let me go ahead and scroll down here to the bottom where I have another instance of that. So this is the original position here, and it's going to end up in a position like this when it is loaded. So we have our force here, that's P. We have some point displacement out here. I'll call that delta sub B. And we're going to have displacements here like this. This is delta sub F. And a displacement here that is delta sub D. Now, we know these horizontal dimensions here. So if we go through and do this, then that is 30 centimeters. This is 30 centimeters. And this is 30 centimeters. So we can use similar triangles in order to write our geometric compatibility relationship. We could take this triangle here, and we could say that delta B is to 90 centimeters and then we take this triangle here, and we could say delta B is to 90 as delta F is to 60. And then we could even go one more and look at this triangle here. And we could say that that's similar to delta D over 30 centimeters. So then we end up with this relationship, which gives us a relationship between the displacement at point F and the displacement at point D. So we could say that the displacement delta F is equal to 60 over 30 times delta D, or we could say that delta F is equal to 2 times delta D. Now, if we go back up to the top, we could look at the original image and we could see, let's see here. Let me go ahead and erase that balloon. And we could see that this displacement here is going to be equal to delta F, but delta F is also equal to the amount of stretch that you get out of wire EF. And that's equal to PL over AE for wire EF. We could look at this displacement here. That is delta sub D, but delta sub D is equal to the amount of stretch that you get out of wire CD, and that's equal to PL over AE time for wire CD. So this is the constitutive relationships, and what I'll do is I'll bring those down to where we were working a minute ago. So we have delta F, that's equal to PL over AE for wire EF. And then we have 2 times delta sub D, which is PL over AE for wire CD. So the next step here is to expand this a little bit and start substituting in our values. So I'll just expand this on the left. We have P sub EF, L sub EF, A sub EF, and E sub EF. And then this is equal to 2 times P sub CD, L sub CD divided by A sub CD, and E sub CD, like that. Excuse me. So now what we can do is a little bit of substitution. We can, let me solve for one of these member forces first. I'll solve for P sub EF. So I can come in here, I could say that P sub EF is equal to 2 times P sub CD times, let's see here, we're going to have the ratio of A sub EF to A sub CD. We're going to have the ratio of E sub EF to E sub CD. And then we're going to have the ratio L sub CD to L sub EF, just like that. So now we can start doing our substitutions. So let me bring that down a little bit further. So this is going to be 2 times P sub CD. And then we're going to have for wire EF, let's see, wire EF is made out of magnesium, has a diameter of 3 millimeters. So this is going to be pi over 4 times 3 millimeters squared divided by pi over 4. And then for wire CD, it has a diameter of 4 millimeters. Then here, let's see, we have E sub EF. E sub EF is 45 gigapascals, and E for wire CD is equal to 72 gigapascals. The length of wire CD is equal to L1, that's equal to 40 centimeters, and the length of wire EF is equal to 30 centimeters, like that. So if we recognize that, these cancel, let me do that in red. These cancel here with that. And if we push through the algebra, then what we would end up with is P sub EF is equal to 2 times P sub CD. And then these ratios, the units all wash out. We end up with 0.4688 here. And then if we multiply by 2, that's equal to 0.9375 times P sub CD. Or we could write it the other way, and we could say that P sub CD is equal to 1.067 times PEF. Okay, earlier we wrote the statics equation, and I'll write it again here. From the sum of the moments, we wrote the equation that P sub CD times 30 centimeters plus P sub EF times 60 centimeters is equal to P, the applied load, times 90 centimeters. I brought the P over to the other side, so it's positive now. So then what we can do is divide this through by 30 centimeters, and we get that P sub CD plus 2 times P sub EF is equal to 3 times P. Or we could divide through by 3 if you want to, and get in a slightly different form. But what we're going to do now is we're going to take this equation and we're going to substitute into the other. And what we'll end up with then is 1.067 times P sub EF plus 2 times P sub EF is equal to 3 times P. And then finally we can, let's see here, add that together, plus we can get P sub EF is equal to, let's see, 667 plus 2, and then 3 swap divided by is equal to 0.9783 times P. And then we can go back up here and we could say that this is equal to 0.9375 times P sub CD. We're just substituting in from here, and that's equal to 0.9783 times P. So 0.9375 divided by, so P sub CD is equal to 1.043 times P. Okay, at this point, we need to look at the stresses in the section. So I'm going to start off by looking at the stress in section CD. So sigma sub CD is equal to P sub CD divided by A sub CD. And if we go back to our problem definition, we could see that wire sub CD has an allowable stress that is equal to 200 megapascals. So what we can do then is we can push the area to the right-hand side. So we could say that P sub CD has to be less than or equal to 200 megapascals times the area. So we have pi over 4 times the diameter of the wire squared. And for wire CD, it has a diameter of 4 millimeters. So then we can say that P sub CD is equal to, let's see, 4, so 4 times pi. And then I convert 200 megapascals to 0.2 gigapascals. And that gives me 2.513 kilonewtons. But we know that P sub CD is equal to 1.043 times P. And if we substitute that in, then we can substitute for the magnitude of the applied load that would cause that wire to fail. So 1.043 divided by, we get that P would have to be less than or equal to 2.410 kilonewtons. Okay, let's look at the stress in wire EF. Sigma sub EF is equal to P EF divided by the area of the wire, A sub EF. And that has to be less than or equal to its allowable stress, which is 175 megapascals. So if we do this again, we can say that P sub EF has to be less than or equal to 175 megapascals times its area, pi over 4 times 3 millimeters squared. So what I do is I'll take 0.175 times pi divided by 4 times 9, and I get 1.237 kilonewtons. Then let me scroll back up here. I know that wire PEF is equal to 9783 times P. So I could say 0.9783 times P is equal to P sub EF, and that has to be less than 1.237 kilonewtons. So then for this, I get P has to be less than 1.264 kilonewtons. So between these two different candidates, a load of 2.4 kilonewtons will cause failure of wire CD, and a load of 1.26 kilonewtons will cause a failure of wire EF. So it works out that this one governs because it's the load that would be achieved first, and that represents the strength of the system.